Okay, so here's our graph of position versus time, right? My position smoothly changed from -1 to +1 in 2 seconds. What if I wanted to tell that same fascinating story with a velocity time graph? What would it look like? And then just picture in your mind that really fascinating journey, that 2-second video of me walking in the positive x direction at a constant speed of 1 meter per second. What's my velocity?
Wouldn't it just be a constant value?
Yeah, it'd be a constant value of like 1, right? So wherever 1 is on this axis up here, let's say that that's 1 right there. It's just going to look like that, right? Just a flat horizontal line. Everybody see that? Okay. If I want to move these things together here, let me see if I can do this. Hope this goes the way I thought it was going to go. We'll see. Oh, it's not. Oh, man, come on. Let's try it again here. Oh, I know why it's doing it. There we go. Okay. There. If I overlap these two things, we can see the relationships at the same time then. How do we connect those two pictures? How are they related? How is the red graph related to the blue graph? There's a connection there.
The blue graph?
Yeah, right? The slope of the blue graph is equal to the value of the red graph, isn't it? Everybody see that? Okay, why would that be the case? Well, think about, see if I can undo that now. There we go. Think about what are the units going to be? Let's just look at this in terms of like a dimensional analysis for a second. We're going to measure position in meters, right? And we're measuring time in seconds. Okay, so if I look at a slope of this line right here, if I'm going to define slope for the blue line, slope is always equal to rise over run, isn't it? Normally it'd be delta y over delta x, agreed? Well, what's it going to be here? What's my rise this time? I don't have a y for my vertical axis. I have an x, right? So my slope is going to look like change in x, which is position, over, instead of a delta x on the horizontal axis, I've got a delta t, right? So that's my rise over my run. What does that sound like? Change in position. So that's going to be my change in position is how many meters did I change divided by how many seconds did I change. Well, that looks an awful lot like a speed or a velocity, doesn't it? Right? Everybody see that? So yeah, the slope of the blue line gives us the value of the red line, doesn't it? Right? Okay. Let's see if we can extend that definition. Okay, if I go back a page to these kinematic quantities, well, velocity, we can see right here, right? Velocity is the change in x over change in t. That's going to be the slope of the position function. What about acceleration? What do you think the relationship is between acceleration and velocity? What do you think the acceleration graph would look like here? Acceleration, we're all familiar with what acceleration feels like, but can we define it, right? So if we...
There be just a constant value at 0?
Yeah, Because am I accelerating? What is acceleration? When do you experience acceleration? If you're driving in your car along a straight road, you only feel the acceleration when you're speeding up or you're slowing down, right? Otherwise, you don't feel any acceleration. So acceleration is what we associate with a change in velocity. And the relationship between velocity and acceleration is identical to the relationship between position and velocity, right? So velocity is going to be the slope of a position time graph, right? Delta x over delta t, rise over run. Well, look at this. Acceleration is the slope of a velocity time graph. Okay, so if we go back and we look at the velocity time graph, well, that just has a slope of 0 the whole way. And so the acceleration here is equal to 0. Okay, are you starting to put this together a little bit, these connections between these kinematic quantities? Let's try another story. Okay, let's try a more complicated story this time. How about one like this? Are you guys seeing? You're seeing the room, right? Okay, so here's my new story. I'm starting at, this time I'm going to start at the starting line. Yeah, I'll start at the starting line. Okay, which is at the pencil sharpener. And I'm starting from rest. Okay, when I say go, we're starting the video camera. Okay, ready, go. And then I start running. I'm just going to pick up speed the whole time. Okay, that's my picture. All right, there's the video that we just took. Let's describe that. Let's draw all the kinematic graphs that go with that one. Okay, what do you think the position time graph might look like? And let's see, get some other people contributing. I don't care if it's right, but I just want to know, what do you think it might look like? Let's take a couple key points maybe. I started off, I was at rest at the starting line, right? So wouldn't that be a point right here? Right? And as I moved to the right, I was picking up speed. Andy, what do you think that graph's going to end up looking like then?
Would it be like a parabola?
Okay, yeah, parabola. So it's starting flat and it's picking up speed like that. Everybody agree? Okay. Now, what about the velocity graph then? Andrew, what do you think the velocity graph is going to look like? If I'm, and I'll tell you, let's assume I was picking up speed uniformly. Go ahead, say it. It's linear, okay. So it's going to look, maybe I start with a speed of what? With a velocity of what? 0. And I end up with a velocity of whatever. After 2 seconds, say I'm going 2 meters per second. Okay. So maybe that looks like that. I'll do that again. That's not very straight. Okay. Something like that. So what do you think, Caleb, the acceleration looks like then?
I have no idea.
Okay. If I was uniformly picking up speed or increasing my velocity, what's our relationship going to be here? We said that, didn't we look at the slopes? Right? Let's make this comparison here for a second between the slope of the blue graph and the value of the red graph. Right? If I were going to look at at like the slope of this curve here, that's a weird concept, right? What's the slope look like down here? Well, it's pretty small, isn't it? Right? If we think about an ant walking along this function, that's not a very steep hill, but the hill is getting steeper as we go, isn't it? So that's the concept we want to by the end of the day, that's what I just hope to be able to make a familiar idea to you, something that resonates and makes sense. As the slope of this thing increases, the value of the velocity function increases. Well, what's the slope? Describe the slope of the velocity function. What is it? I mean, we don't know what the number is necessarily, but how would you describe that? What do you think? Daisy, how would you describe the slope of that red line? Is it positive? Is it negative? Is it changing? Is it constant? What do you think?
I don't know. Looks positive.
It's positive for sure. Is it changing or is it constant? It's supposed to be. Ignore my crappy drawing, but it's supposed to be constant, right? So it's positive and constant. And so then what do you think the acceleration graph should look like, right? We said that the value of the velocity corresponds to the slope of the position. The value of acceleration then corresponds to the slope of velocity, right? If the slope is positive and constant, what's my green acceleration graph going to look like here, David? Positive and constant. Exactly. It's positive and constant. So it might just look something like this, right? Well, I guess I don't go that far. It stopped right there, maybe, right? Get the idea? Okay. All right. We'll come back to this. We'll come back to this in a little bit, but I want to define something for you now. We'll get back to our kinematics discussion. Just in general, we say in math that a secant line is a line that intersects a curve in two places locally. It might incidentally intersect the curve in other places also, but let's say that we know we have a function that has a value of x, f of x, and it has a value of x plus delta x, f of x plus delta x, if we move to the right by delta x. Okay, everybody see that? So there's my x value, there's the value of the function at x, and if we scoot to the right of our original x value by some amount we're going to call delta x, then this x value right here, right, if I want to write these on the graph, here's an x value of x, and then if that's delta x, this is an x value of x plus delta x. Remember, delta just means change in. So here's x plus whatever the change in x was. So that means that the y value here is whatever I get when I plug that into my function. So it's just f of x plus delta x, right? Okay, well, the secant line is intersecting the curve in places. If I draw a line through those two intersections, what do you think the slope is telling me of that line? Right? Slope is just rise over run. So the slope between this intersection, we could call delta y, or the change in the function, right? We'll just call it delta y for rise. The change in x, we already called delta x. So we can see then that the slope of the secant line is just equal to delta y over delta x. Well, delta y over delta x, that's just going to be this y value, which is f of x plus delta x, minus this y value, which is f of x, divided by delta x. That's what we call the difference quotient, and that's how we define the slope of a secant line. What's it telling me, though, for this function? What's the slope of that secant line telling me about the behavior of the function between x and x plus delta x? Can anybody describe that? How could we use some math words to describe what that's doing? Right? I'm going to throw some at you here. See if this makes sense. The slope of that secant line is telling us what the average rate of change of the function is on that interval. Right? It's telling us how much did the function change compared to how much did the x change, right? So the slope of a secant line we always associate with what we call an average rate of change. This is not a calculus concept, right? This is a pre-calculus concept. We don't need any calculus. No, we haven't even really learned any calculus. We don't need any calculus to understand this. It can be really useful. Here's an example. How long does it take a car traveling with an average speed of 60 miles per hour to travel 150 miles? Well, Everybody do that one in your head. How long does it take a car traveling with an average speed of 60 miles per hour to travel 150 miles? What do you think? Anybody got an answer? Amber, you said something. What's your answer? Yeah. How'd you get that?
I just divided 150 by 60.
Okay, good. So let's go ahead and make a picture, kinematic picture describing that. How about? Okay. How much time we got? Man, I really want to get through. I wish our classes were a little longer. Oh, okay. This is where we're going to probably have to end up. But so if this is position, let's say we're traveling in a straight line. We're in the Midwest and we're traveling in a straight line the whole way. So we got X versus T. We know that we're starting off here at the starting line. And after 2.5 hours, so there's 1, 2, 3. So after 2.5 hours, we're going to be this far away. That distance right there is 150, right? So we're going to go from this point to that point. Everybody agree? Okay, so what does this description here says if the average speed is 60 miles per hour, then we're going to get from here to here, and the input value is 2.5. Okay, so what does that look like? Well, it could look like cruise control the whole way, couldn't it? Cruise control on 60. And what's the slope of that line? 150 divided by 2.5. That's going to be 60, isn't it? Right? That's my slope. Does it have to look like that, though? Did I have to have my cruise on the whole way? No, not really, right? Couldn't I have done this? Maybe I just accelerated really slowly the whole time. Maybe I started off at 0 and I gradually picked up speed the entire 2.5 hours, and I was going my fastest when I got to my finish line. Everybody agree? I still end up connecting the same 2 points on my position time graph. But my speed, right? Wouldn't you agree on my speedometer? It's got a low value there, it's got a medium value there, and it's got a really high value there. But the average rate of change here is the slope of this secant line. So the slope of this blue line that's connecting those 2 points is giving me my average speed. Is it telling me that that's exactly the speed I'm going the whole way? Absolutely not. In fact, it could be much more complicated. Maybe I'm doing something like this where I pick up speed and I lose speed and I pick up speed and then I stop there for a while so my position doesn't change and then accelerate to the end, right? It could do all kinds of things. But once again, as long as I'm connecting those 2 endpoints, the slope of the secant line is telling me my average speed for the trip, okay? All right, so let's consider the case here of what if we have a planet with no atmosphere and we're going to drop, so it's a rocky planet with a surface, and I'm going to drop an object from some height on that planet. What is the position time graph going to look like, first of all? What do you think? Isaac, what do you think the position time graph is going to look like? If I'm starting off, well, you know what the starting position is, right? So this time it's vertical movement, but it's still movement in a line, right? I'm just dropping an object and it's falling vertically from some high value.
It should be like constant straight line, like diagonal slope down, right?
Okay, so after some time, the position's going to be 0. So I've got to connect those 2 points, let's say. Okay, so is it going to do, Isaac's suggestion is it's going to do this. Is that what happened? Well, the Earth is an example of a rocky planet. If I drop an object off of, say you drop an object off of your house, does its position change uniformly? So for example, let's say you drop an object, just imagine this, you have to kind of use your imagination. Say we drop an object that's coated with sliprium, and that's a really expensive product. but we can code an object with that, and there's no resistance at all. You get it at the Acme store. Extremely expensive, but we'll eliminate all air resistance, right, if we coat this thing up with slip rim. So we drop this thing and it falls for 4 seconds off this building. After 2 seconds, do you think it's gone half the way to the ground? Yes or no? Give me thumbs up, thumbs down. Thumbs down, yeah, because when is it going to be traveling the fastest? At the start or the end of its journey? Okay, I'm seeing at the end, right? So this would imply here that when we're halfway to the ground, it's taken half the time. So I'm not buying it. That's not consistent with what we see on Earth, right? So I want a different answer for that one. There we go. So we're starting here and we're ending here, but what's the path going to look like? What do you think, Johan?
Wouldn't it be like a curve?
Okay, so it's starting steep or it's starting flat? Flat, right? Because it's starting, as time progresses, it's not changing its position very much, is it? Right? It's just doing something like that, and it's picking up speed, and now it's starting to cover more ground per increment of time. Does that make sense? So if we're looking at position versus time, that's what maybe it looks like? Everybody agree? Well, let's change this, though. How about if we're measuring, okay, just to be consistent with my next slide, let's say that we're measuring the distance that it's fallen from you, right? You're dropping it from the building, and so the distance is increasing. So in that case, maybe it actually looks like that, right? It hasn't fallen very far at all, but after a while, it's fallen a long ways from you at the top of the building. So we're measuring distance it's fallen from your perspective. Make sense? Okay. What if we want to measure let's put some teeth to this, and let's ask ourselves, okay, what if we want to find, we'll actually pretend we have a function. What if I want to find the average velocity of this object between 2 and 5 seconds? What could I do? So I've got this function that I could graph, right? And I'll pull up Desmos. And I know I have this on Desmos somewhere. Yeah, there it is. Okay. So this is my position function now. Okay. This is how far it's moved in a line as a function of time. Right. So there's my position function. This is S is on the vertical axis and T is on the horizontal axis, right? And we're really only interested between 2 seconds and 5 seconds, right? So we're interested in that point. After 2 seconds, the object has a position of 1, and we're interested in this point. After 5 seconds, it has a position of 8.5. If I want to know the average velocity of the particle, I just want to know the slope of the line connecting those two things, right? Okay, well, that's just this line. Nope, not there. It's that line right there, isn't it? There's my secant line. Okay, what's the slope of that line? Well, that's just going to be, rise over run. So it's going to be 8.5 minus 1, which is 7.5 meters, divided by 5 minus 2 is 3. 7.5 divided by 3 is 2.5, or 5 halves, right? That's my average rate of change. Everybody agree? Okay, to find that, do I have to have a graph? No, I don't need a graph. I could just do this, right? If I want to know the average velocity is just going to be S of 5 minus S of 2 divided by 5 minus 2, right? Because isn't that just equal to S of T plus delta t minus S of t over delta t. Okay, we'll wrap this up next time. This stuff takes a while. Give me a 1 to 5 real quick though. Is it starting to make a little sense? Okay, and if you're 3 or above, I'm pretty darn happy about that, honestly. I mean, this is some pretty big concepts. All right, we'll hit it next time. Have a great day.